Today I will restrict myself exclusively to spheres. And when we deal with spheres, we're going to get that the force, the magnitude of the force, so that's this part, equals C1 times R times the speed plus C2 times R squared times V squared. And again, it's always opposing the velocity vector. C1 in our units is kilograms per meters per second, and C2 has the dimension of density, kilogram per cubic meters. We call this the viscous term, and we call this the pressure term. The viscous term has to do with the stickiness of the medium. If you take, for instance, liquids, water and oil and tar, there is a huge difference in stickiness. Physicists also refer to that as viscosity. If you have a high viscosity, it's very sticky, then this number C1 will be very high. So this we call the viscous term, and this we call the pressure term. The C1 is a strong function of temperature. We all know that if you take tar and you heat it, that the viscosity goes down. It is way more sticky when it is cold. C2 is not very dependent on the temperature. It's not so easy to see why this pressure term here has a V square. Later in the course, when we deal with transfer of momentum, we will understand why there is a V square term there. But the R square is very easy to see, because if you have a sphere and there is some fluid, gas or liquid streaming onto it, then this has a cross-sectional area which is proportional to R squared, and so it's easy to see that the force that this object experiences, we call it the pressure term, is proportional to R squared. So that's easy to see. Two liquids with the very same density they could have very different values for C1. They could differ by 10 orders, not 10, by 4 or 5 orders of magnitude. But if they have the same density, the liquids, then the C2 is very much the same. C2 is almost the density rho of the liquid, not quite, but almost. But there is a very strong correlation between the C2 and the density.